Good morning and welcome to today's invited talk session. We are very excited this morning to have Ben Mildenhall with us. Ben obtained his PhD in computer science from UC Berkeley in 2020. From 2021 to until recently, he was a research scientist at Google Research. Ben is a pioneer in the area of neural radiance field. His research had a large impact in areas such as, for example, inverse rendering and view synthesis. He's been the author of very seminal work in this field. Just to name a few, NeRF, DreamFusion, ZipNeRF, MIPNeRF, and so forth. It's hard to name them all. His research work received several awards at best computer vision conferences such as CVPR and others, as well as other prizes such as the David Sakerson Memorial Prize. We're very excited to have Ben with us today. Thanks for being with us, and the stage is yours. Thank you.
Okay, thanks very much for the nice intro, Federico, and of course for the invitation to speak here to all of you, and thanks to those of you who are here before I was at 9 a.m. To reward you, there's a stupid pun as the title of my talk, which will become somewhat clear, hopefully, as I go through my slides. I think, luckily this is 3DV, so I think we're all on a shared page here about the importance of 3D and a common interest in that research field. I don't have a bunch of slides explaining why 3D is important to me personally here, but I have a few sprinkled throughout the rest of the talk, just to jump right into what I want to talk to you all about today. So I will talk a little bit about NeRF, but not just the what's in the paper, but a little bit of the process of coming up with the work itself and kind of the motivations behind it, what we've been doing before, and how the actual process of doing that research project occurred. And then I'll get into some more recent work that I was doing with collaborators at Google, more along the lines of not only reconstruction, but also generation, right? Not just reconstructing what we've observed from some captured input images, but trying to actually create content, from some underlying distribution of how we believe 3D things are represented in the world. And first I'll talk about DreamFusion there, which I think you can loosely interpret as generation via reconstruction. And then our more recent work from last year, ReconFusion, which I think kind of flips that around and can be viewed through the lens of reconstructed as aided by a generative prior. Okay, so first, just very, very quickly, what is NeRF? What is the kind of basics underlying the NeRF algorithm? Of course, you start with some input images and poses. This is a view synthesis algorithm, right? So we fundamentally want to take some input images capturing a scene or an object and reconstruct some 3D representation and then render new views. So we assume that we have given input images and their calibrated camera poses. We sample random rays through those images. We sample 3D points along those rays. We pass them through the underlying 3D representation, get output color and opacity. We use volume rendering to composite those down onto output pixels. And then we kind of use this render and compare loss, right? We take the output color from NeRF, we compare it to the observed color in the input images, and we just simply apply an L2 loss with gradient descent. And of course, as we all know, this converges to fairly successful scene reconstructions for these synthetic objects, and also in the original work for these kind of limited baseline forward-facing scenes. Okay, so I think that's probably all I need to roughly say about the actual algorithm itself, but I wanted to give some background on kind of why this happened when it did in our group. So I was a PhD student at Berkeley starting from 2015 in Ren Eng's group, and Pratul Srinivasan was also a student there. He started in 2014 with Ravi Ramamurthy and then became co-advised with Ren after that. And starting around 2017, me and Pratul worked very closely together for the last 3 or 4 years of our respective PhDs. And Pratul had this background in working on light field analysis and synthesis because of both Ravi and Ren's shared interest in this topic. And we kind of noticed this trend going on as we were working on this area, that a lot of work was starting to focus on the kind of promise and potential of volume rendering as a very effective, differentiably optimizable representation for scenes, especially when focused on very high quality image synthesis, not just underlying 3D reconstruction. And there are a lot of notable works from 2015 to 2020 in this area. Just to pick out a few that were sort of fairly influential on our own thinking. In 2017, there was this work, soft 3D reconstruction for view synthesis. This was from a couple of, I think, engineers at Google. And it was kind of like one of the last gasps of these very well-tuned heuristic kind of multi-view stereo-inspired methods, right? They constructed cost volumes, they had hand-tuned heuristics for matching those and creating these kind of soft volumes, and they actually achieved, honestly, I was looking at the results last night, really stunning, even to this day, view synthesis results from this kind of method. Though a lot of the results were limited to fairly small baseline. And then after that, we had Tinghui Zhou and colleagues work in Noah's group at Google on stereo magnification using multipoint images. This is a SIGGRAPH 2018 paper. And they borrowed this representation, which I think had been used by Rick Zalewski and others in the 90s, this kind of like originally stack of acetates and then later renamed multiplane image representation that's just a simple stack of RGB alpha planes that you composite front to back. And this proved to be a very, very effective representation for predicting from a CNN in a feed-forward manner, just supervised by image-based rendering. And finally, there was this kind of almost mind-blowing work in 2019, this neural volumes work from Stephen Lombardi and colleagues at Meta and the Reality Labs research group, where they reconstructed a single scene at a time, and not just static content, right? They had multi-view dynamic scene capture in 2019 with these like very, very high quality dynamic renderings of human heads talking, and like they had this like dry ice with the smoke coming out of it, and all these other like very fine like non-surfacey details showcased by what they could do with volumetric rendering. So especially after stereo magnification, in like 2018, 2019, me and Pertul were very invested in moving into this kind of representation. We had worked with a sort of deep stereo type thing before with a cost volume and like an expected depth distribution, but the clear promise of alpha compositing from stereo magnification motivated us to switch right away to that type of representation. And so both Pertul and I had some follow-up works the next summer from our internships that we did. The one that I did at Fusion was this local light field fusion paper, where we combined a bunch of multiplane images together to expand the potential baseline for view synthesis, right? So on the left, I'm showing one multiplane image. On the right, it's what you can get if you combine the renderings from 25 different multiplane images together to achieve wider baseline. And of course, this is, was called local light field fusion because we sort of pitched it that each multiplane image is like a tiny light field approximation. And this has some sort of similarities to a lot of light field interpolation works from many, many years prior. And besides the volumetric rendering thing, there was a huge boom in 2019 of these computer vision papers using MLPs to represent 3D signals. It was almost this like concurrent explosion of works, right? There was, I'm sure you all remember, deep SDF, occupancy networks, among others. I think maybe both at CVPR 2019, and then some follow-ups. So those original works were focused on just pure 3D geometry reconstruction and representation, right? DPSDF and occupancy networks trained directly on ground truth data from ShapeNet and other 3D data sets. But then even by the end of 2019, there were multiple works that supervised this type of representation from re-rendering loss alone, right? To name a couple, there's differentiable volumetric rendering from Andreas's group led by Michael Niemeyer, and there was Vincent's work in Gordon's group on scene representation networks. And both of these had this common setup where, they were saying, we don't want to have to supervise from 3D ground truth shape information. We wanted to reconstruct this kind of representation from just images. And another aspect of these papers that was, they often included kind of like an inspiring or motivating toy example of training on a single scene, right? Almost all these papers were trying to generalize this kind of thing across a whole ShapeNet category, like ShapeNet cars, ShapeNet chairs, and learn a latent code per object and things like that. But Deep SDF has this kind of initial figure showing we can reconstruct the Stanford bunny in a single MLP and get this kind of nice shape out of it. So that was another thread that was emerging. Okay, so that was kind of the lead up to us starting this work. And how it actually happened was, I remember that we did the very first experiment on a Friday afternoon after winter break in Berkeley. We had a kind of frustrating fall semester, not making very much progress, and then we kind of switched over to this MLP thing after winter break vacation. And then we had about 2 months from there until the ECCV 2020 deadline. So I actually went back and reactivated our group's dead Slack and pulled a couple messages and results from that time to kind of see what the course of progress looked like as we were working on this. So yeah, as I correctly remembered, the first messages were from like Friday and Saturday, that January 3rd and 4th, where I remember sitting in the office with Pratul and Matt, and we were talking about, oh, there's all this like MLP stuff. Should we be doing this? Like, is there something we can like integrate our volumetric work in with these like MLP-based representations? And we, of course, we've been working on this for semesters and years, basically. So we had tons of multi-view data sets, all the code set up to do volumetric rendering, and it's obviously not actually a very sophisticated implementational change to switch from querying an underlying 3D grid to querying a 3D MLP, right? You just take that coordinate, instead of indexing into the grid, you just send it straight through some like pre-baked MLP module, in our case in TensorFlow, sadly. So yeah, this was like the first scene that we tried. I've been using this for a bunch of voxel grid-based experiments, this baked out Stanford bunny data set. And it, to our surprise, within like 2 hours of trying to do this, just sitting there in our office messing around before we were about to go home for the weekend, we managed to get a pretty decent Stanford bunny result. And then we kind of pretty quickly migrated over to other types of scenes, right? So we had a bunch of ShapeNet objects lying around because the entire previous semester we had been trying to work on finding a way to directly optimize sparse voxel grid representations, mostly in the form of octrees. So we were getting really frustrated with all this stuff. We were saying, oh, we can't like optimize with greedy heuristics for split decisions on the volume because we're going to fall into all these local minima and like misfind structures and stuff, which later proved to be, of course, totally wrong when people revisited this idea. But we got kind of like obsessed about finding some kind of reinforcement learning or policy gradient way to get around these non-differentiable decisions of sparsifying a grid structure. As a result of that, we had a ton of these kind of ShapeNet renderings, multi-view 360 ShapeNet images, and we ran one of those through, and it's not just this kind of, it has these concave geometric features, right, that were still able to be reconstructed pretty well from this representation. So that was a nice sign of life as well. And then, straight after that, essentially we were like, okay, it works okay on objects, but most of our work before this had been on these forward-facing real scenes, and we were like, oh, haha, there's no way it's going to work on that. But then, we tried it, and it worked to the extent that you would say, oh, this is an interesting toy example, right? You got this kind of blurry fur now. It's clearly 3D consistent, but it's not yet at the point where you would think, oh, yeah, this is like a real feasible method for attacking this problem. It's more still on the research kind of side. I also, as soon as we started working in this kind of MLP formulation, a lot of the natural consequences that ended up in NeRF like follow very immediately from that, right? Like sort of random ray batching idea immediately emerges, as opposed to outputting a grid directly from a CNN where you can't really easily output sparse individual pixels. With the MLP-based formulation, you're just querying points to the MLP. You don't have to worry about the entire volume. You can immediately jump to stuff like random ray batching out of higher res inputs. And another aspect that fell out immediately from that was this idea that you're no longer tied to some underlying discretized resolution that actually limits the reconstruction quality. And along with that, you're not tied to this like alpha compositing in 0 to 1 alpha range. And in fact, we very quickly stumbled on this idea that like you might actually want to refocus samples more tightly around where the scene content is. And as a result of that, you actually have to switch from an alpha-based model to this unbounded above sigma density rendering model, which is, of course, this, is equation 1 in the final paper, right? Introducing or reintroducing from traditional computer graphics this kind of extinction absorption volume rendering model with a sigma instead of an alpha. This one I thought was just kind of funny. The next day I was still like, I don't know if this is really anything worth pursuing. Like the scenes are so blurry. We'll see how it goes. But yeah, we started seeing some signs of life pretty quickly that there was some interesting potential around particularly the aspect of this where you can optimize a scene over every single input image you have of the data set, right? We were all kind of like working in this mental framework of feed-forward models for view synthesis where you're very restricted in terms of the amount of input memory you can use, especially when you have an output 3D representation where you don't just have this like n squared, you have this n cubed resolution scaling that really prevents high quality in a voxel grid that you're directly predicting at the time, at least. So we were seeing, oh, you're getting kind of very nice like global scene structure that's totally coherent from optimizing over not just 5, but 25, 50 input images in this case. And the thing we're discussing here is like for these very fine geometric structures, in our previous work that optimized feed-forward networks over 5 input images, you would often get kind of mistakes. As you transition between different MPIs, they would all have different geometry predictions, and as you blended between the outputs, you would get this kind of flickering. It maybe is like a little bit subtle, but it really bothered us, right? The fact that we didn't have a global representation that was completely temporally coherent for the entire scene. And fairly soon after this, we kind of, per tool, integrated one of the other, what ended up being core components of NeRF, right, this view-independent aspect. So we've been working again with these 3D gridded representations where you have this kind of cursive dimensionality with 3D. But as soon as you move to an MLP, you're kind of unbounded by that, right? You can feed anything you want through it. You can feed latent code, you can feed view directions, like it doesn't matter, right? You're sort of decoupling the complexity of the input space and the dimensionality of the input space from the actual like memory requirements of the underlying representation. So this is a type of visualization that I hadn't realized that Pertool made this so early, but we ended up using some of these in the video for the final paper where it's not a physically possible rendering to achieve in the real world, but you fix the camera and then manipulate the input viewing directions to the network to expose, okay, keep the geometry static, what has been actually clearly factored into the view-dependent radiance of the network. And you also see at the bottom here, Pertool's kind of proposing what ended up being actually the final architectural setup of the NeRF network, where you have this first module that predicts density, and then a second module that takes in the view direction and predicts color. Another thing that we were used to with these kind of volume grid representations before was both seeing very small baseline input to the network, and also seeing a lot of artifacts from not using any view-dependent effects. So like, MPIs are just this like 3D RGB alpha volume grid representation, and they'll often achieve this like what looks like a good visual result, but it's actually exploiting a kind of like, not flaw, but choice in the rendering model where it can carve a hole in a low texture shiny surface to place specularities at a virtual depth to achieve like this shiny effect, even though there's no underlying specular capability of the rendering model. And this is an example of that from John Flynn's deep view work that predicted MPIs in a feed-forward manner with learned gradient descent. So on the left, you can see there's this like shiny white specularity on the bottom right-hand corner of the rendering, but that actually corresponds not to a flat floor with a view-dependent appearance. It corresponds to a deep hole in the floor with a white patch placed at the back of it and some kind of fuzzy geometry on top to make it all look correct. Another natural conclusion from switching to the MLP is you can just feed in time if you want. So this was one of the neural volumes data sets that at some point in January or February, I ran this through with time as an input to the MLP. And of course, that thing, it works decently well if you expand the capacity of the MLP to be able to incorporate more data. And then, of course, like kind of the main next step that turns us from a toy curiosity into something that was actually practically feasible as a competitive view synthesis method was the additional positional encoding to the MLP. So this, I guess, in the end came about 2 weeks after the original experiments. I think we were all, me, Pertool, John, we're all sitting around in a room discussing our frustrations around like not finding a way to circumvent the fact that the network always just hit this kind of like upper bar of frequency content. Even if you just try to represent a single image in an MLP mapping from pixel to RGB coordinates, you would, even if the MLP was like 10 times larger in terms of weights than the number of pixels in the image, you would never actually recover fine details in a reasonable amount of training time. And this seemed just like intuitively wrong, right? Like, everyone talks for years about how networks and MLPs are universal function approximators. Like, why can't we find a way to make this thing learn this image that's clearly like within its capacity to do? So we were talking about, oh, maybe this like, you're effectively feeding this low frequency kind of mesh grid ramp of coordinates through the network in the case of the 2D image very directly, right? You're mapping from mesh grid to output RGB image with all the high frequency content that entails. So we were talking about, oh, maybe we should just feed some higher frequency content into this thing and see what happens, right? Maybe, we should put like the binary representation of the number, like the sort of coordinates in an octree, like, oh, that's the same as like a triangle wave or a square wave, or sine and cosine. So we had that meeting, and then it's super easy to try, right? It's like a 1 or 2 line change to the code. Matt went and tried it straight away on the images and was like, guys, look at this. This is crazy, right? He showed us this insane plot of PSNR, and this is probably a few minutes of training for image memorization. And we were like, okay, this is pretty wild, right? Like, this is something to get into here. We went and, of course, straight away tried to apply it to the 3D stuff. There was some amount of, regularization, and like we added too many components and got all this like high frequency aliasing and stuff like that. But after a couple of days, we managed to dial it in such that we were getting, much higher frequency content recovery without any too nasty, spurious artifacts in the 3D reconstructions. And then, yeah, so we had results, on a bunch of LLFF scenes of these forward-facing real captures. And this was me sending one of them to John, and also emphasizing part of what became kind of the final pitch in the ECCV submission around, okay, these MLPs are actually a very effective form of direct differentiable scene compression, because, any kind of explicit 3D grid, whether it's an MPI or just like a regular Euclidean space grid, has this n-cubed scaling problem in terms of data. But the MLPs have effectively decoupled that in a way, and like part of the capacity is due to the positional encoding, part of it is due to the underlying weights, but it's sort of factored out in this directly compressed way that lets you learn without instantiating the entire volume at any point. And then, those were not too far from the results that ended up in the final paper on March 5th. And we actually essentially got distracted by a bunch of rabbit holes after that, pursuing like various directions of things we might want to add on top of that for the paper. A very large amount of effort went into trying to figure out some kind of justification or theoretical explanation for why positional encoding worked. We ran unbounded number of experiments in 1D and 2D like this, like making all these plots, trying different encodings. Basically any like multi-frequency encoding worked, it doesn't have to be sine and cosine. We didn't really get at any of the underlying properties of this until after the deadline, though. So it didn't end up in the final paper. We were also looking at, okay, can we find like a whole class of useful applications for these positionally encoded MLPs and target the paper around that rather than just being a view synthesis paper? We were trying to just drop it into a bunch of other stuff like deep SDF, PyFu, SRN. We were trying to see like, can we use it for policies in robotics or like any of these other low dimensional, high frequency tasks. We were trying to memorize videos and stuff like that. Of course, in the end, none of this made it into the final paper. And yeah, just like a laundry list of other things we were looking into. We were like, oh, is there some wavelet basis argument around this? Is there some Fourier basis argument around this? Of course, in the final paper, there's kind of this one, like, I think it's like a 5 to 10 line section that just says, we use this positional encoding thing and it improves results in some ablations. And there's basically no justification for it because we didn't have anything that we felt like really satisfied of delivering to the community as a justification for why this worked until, we had a later NeRF submission on that. And yeah, basically it was just cleanup at this point. We were doing all of the usual work you have to do to get a paper polished. We in particular wanted to have a very defensible submission because we were, we thought this was very promising and we wanted to sort of like preempt any kind of attacks around like view synthesis performance or comparison to relevant baselines. So, Matt in particular did a lot of heroic work getting, deep voxels and like SRN and neural volumes code running on our data. We also, we tried really hard to get 360-degree real scenes to work because we were like, oh, it'd be so cool if we could lift this constraint of forward-facing real scenes, but we didn't get that in time. We were trying all this stuff around like CT because it's kind of analogous in this volume rendering model, but that ended up not really making sense in the context of the paper. And yeah, going back to the baselines and comparisons, so we started running baseline comparisons in whatever kind of single scene optimization frameworks we could find from before. So one of the main ones was Vincent's work in deep voxels and in SRNs. And he had this kind of 4-object synthetic data set that he rendered at reasonably high quality with a lot of input images to target this specific single scene reconstruction task. And we found that we basically kind of like blew the roof off of this, right? We were hitting like 40 dB PSNR for some of the objects, and we thought, okay, we need to like find something that's not going to be so easily saturated given that this works so effectively. And of course, that's what led to this selection of objects. I think these are all just random blend swap objects that Matt was scrolling through, and like we found a couple that we thought demonstrated both geometric complexity and view dependence very clearly, right? We have, Lego bulldozer and the fern or the ficus for very high frequency geometry, and we have stuff like the drums and the material balls for capturing specular effects to kind of probe all of those different aspects of the representation. And at this point, I think even this data set is fairly saturated at this point. I think it's worth, always trying harder examples when you're training a view synthesis method these days. But, it's interesting we still have not quite gotten to this level of quality for the generative methods, We're still not reconstructing, stuff like the drums or Lego bulldozer from a single input image very clearly. And of course, like I mentioned before, we were a little bit frustrated by our limitation to these forward-facing real scenes because we thought, oh man, we've figured out this way to do 360 view synthesis for objects. It would be so cool if we could also show the immediate transfer of that to unbounded real scenes as well and have the full package. So we had not at all addressed in the paper, but we had these two results that we put up on the web page. And this was kind of the compromise after I captured, 10 or 20 of these 360 real scene captures and ran them through. And it turned out that basically it was presentable as long as you don't have the camera tilted up to see too much of the background, right? As long as you can kind of encapsulate this thing in a bounding box, you can get these plausible results. But this, of course, totally falls apart if you lift the camera up and actually show more of the background. So yeah, we submitted that to ECCV on March 5th, and we kind of wrapped it all up for public release on arXiv on March 19th of 2020, which also turned out to be, both a good day and a bad day. That was the day we all kind of went home for good. So it was a bit of a surreal moment to kind of put this thing up and then basically not talk to anyone in person about it for 3 years for the most part. But yeah, at this point, I guess it's just over 4 years from that date, and I just wanted to kind of touch on how things are looking these days, given the original assumptions and constraints we put in the original work. So I think when people talk about NeRF or say, we did a radiance field or this is a NeRF-like method, it can refer to 4 main aspects of the problem. I think one obvious one is using an MLP as an underlying 3D shape representation. One is using an MLP or any kind of representation for view-dependent appearance on top of a volumetric model. One is this underlying idea of single-scene 3D reconstruction, which was, again, like I said, a lot of the community, us in particular, we were focused on these feed-forward methods before, and we almost viewed this single-scene thing as cheating or something that would be hard to explain to machine learning people, even though, obviously it has direct analogies to SLAM and SFM and things like that, but it kind of wasn't in the zeitgeist of computer vision at the time to say, oh, we trained this network on a bunch of pictures of the scene and we render the same scene out. There was some chance we were worried that reviewers would say, hey, what are you doing? You have the same images in the input and output, this is too easy. And then, of course, I think the last and most significant one here is this aspect of using differentiable volume rendering. And I would note that, of course, none of these 4 things was remotely close to being proposed by NeRF. They existed anywhere from 1 year to 30 years prior to us writing this paper. We just pulled them all together in the same place in the same time. So if I'm kind of rating the fallout of all of these things individually, I would say MLPs for 3D shapes, I think, was not the most important or best part of the paper, but I think there's some aspect in which it was a nice stepping stone to kind of get the community interested in this idea of okay, we can directly optimize what is effectively a compressed underlying representation and not need to worry about this dense 3D scaling of memory. And another aspect of MLPs is that they've actually kind of been picked up more as a super conveniently regularized representation, not just for direct 3D density or color, but also for stuff like appearance flow and other signals that actually naturally have a more low frequency character, right? Texture is kind of one of the highest frequency things, but this stuff like tracking and deformable object movement is something where having the natural low frequency regularization of the MLP can serve really well. And of course, this is something that actually was very popularized by the earlier work from Andrea and colleagues at Deep Image Prior, where they showed a bunch of different applications could be done for 2D image processing by just training a randomly initialized UNet to match a target input image. And that target input image, it could actually be corrupted. It could have super strong JPEG artifacts. It could have a lot of noise applied. It could have some chunks missing and needing to be inpainted. And the natural underlying regularizer of the CNN in this case would actually sort of effectively smooth a lot of those things out. And another clip from the Slack here is we were sort of like confused for a while about why are we able to even get away with doing single seam optimization? Because we had tried this for MPIs, right? We took all those forward-facing images and we directly optimized the voxel grid, and you just get, as expected, the training views to look good, but the test views to look like garbage, and they're just full of all this kind of like speckle and fog and things like that. And yeah, like I said, there's also this underlying aspect of MLPs as signal compression. So it can be hard to make network weights compete in tasks like image compression or video compression, where it's been studied for decades effectively and fine-tuned very carefully to work at a very effective level. But of course, these kind of codecs are not natively designed to be differentiable, right? You can't optimize. You can do all this like sort of soft ramp stuff to make quantization backproppable in JPEG or MP4, but these things were really designed with like feed-forward compression and data transmission and a heuristic decoding in mind. They're not a thing you're really supposed to learn through. And in particular, image and videos don't have this other aspect where like they're natively sparse. And that's the thing that really differentiates 3D. Both there was not kind of a go-to standardized 3D compression mechanism that was differentiable, and 3D has this inherent sparsity where like you're usually existing on a 2D manifold through the 3D space. And that gives the MLPs a very kind of competitive advantage. But I would note that, once this becomes more popularized, you do see people bringing a lot of those like dictionary quantization-based efforts to have a more proper compression scheme in place. And I think we probably no longer could claim that MLPs are completely state-of-the-art for this, because there's still this kind of like heuristic method for compression, not a very intentional one. Moving on to using MLPs for view-dependent appearance. Of course, this was just something that emerged from concatenating ray direction coordinates to the network. This ended up being a pretty reasonable idea, right? So I think still to this day, what I mostly see in view synthesis methods that have some kind of specular representation is usually either a small MLP or something like spherical harmonics or spherical Gaussians. It's a more explicit representation of the outgoing radiance. And it's sort of not clear, I think it depends basically on what application you're doing, how much memory overhead you can tolerate for spherical harmonics, or like how much you want to emphasize sharp specularities in the case of maybe Gaussians or MLPs, which of these you end up using. And we were pleased with this result. It's not like a super clean kind of like nice Lumisphere output like you get from an actual factor BRDF and lighting representation, but it very clearly did show that the MLP is learning from a fairly sparse sampling of this high frequency specularity. There's 100 input views here. It's learning that there is this concentrated white highlight that's located at like a reasonable point on the outgoing hemisphere for each of these 2 points in the scene. I think, I've already alluded to this a bunch of times, but I really think this kind of return of the dense per scene optimization framework is a really good thing, right? I feel completely vindicated in saying that because of results like this we can achieve now. I never would have expected this was possible from 2019 until like 3 years later with MIPNERF 360 and ZipNeRF, but this is just something I would never imagine being possible with any of the memory constraints that exist in feed-forward architectures right now, right? You can just scale up this underlying MLP or now like hash grid or whatever base representation and directly use brute force L2 optimization to reconstruct a very, very large scene, right? And this is still only 300 megabytes on disk, I think, even with an underlying spatial hash grid backing it. So I think if you had a similar kind of geometric complexity in a mesh or something like that, it would probably be a lot larger. And I think differentiable volume rendering, I feel very comfortable in saying that is a good thing to use. And I gave this sort of context for NeRF where there had already been a bunch of works that looked into this and were observing that this was a very nice space to optimize in, and I think that's all been carried out over the last 4 years too, to an extreme verification degree, right? We see, even surface-based methods often fold like a small volume around, like, News and Vol SDF. They actually use a volumetric approximation to the surface rendering to get this thing to converge from scratch. And I think just the aspect of being able to kind of instantiate volumetric density anywhere in space and not have to kind of move like a mesh or something around to do the reconstruction leads to these like very, very nice optimization dynamics, right? This is the convergence video from Instant NGP, once they got this down to 2 seconds or something. And I think we have a sort of equivalent one for one of the larger ZipNeRF scenes where you can very viscerally just observe, like, this thing starts from nothing, right? It starts from kind of shallow fog across the entire scene, and then everything just from low resolution to high frequency details, you see everything just emerge, right? Because you're tracing samples through space densely, you backpropagate gradients all the way along the ray, and you're just able to reconstruct very, very high-frequency geometry in that way. Another aspect of NeRF that people sometimes ask me about is like, why do you do this problem? Why do you care about images? Why don't you care about the underlying geometry and all this other stuff? And I think that like that's a little bit of a red herring. And I would say that there's a few reasons that we kind of chose to focus on this. Of course, one was this whole like light field origins that Pertul and like Ren and I were coming from, where it's really this like fundamental RGB visual output focused task. But I would also argue that when it comes to the available sensors that we have right now for capturing visual data of the world, RGB images are really the only thing that's remotely scalable, right? Compare the amount of like R&D and marketing and sales effort that's gone into selling cameras, especially cell phone cameras now, versus anything else like LiDAR or like active illumination sensors or time of flight sensors, and it's just not even close, right? Look at YouTube and anything like that. You just have an insane amount of RGB data compared to any other modality. And a lot of these other, strictly 3D sensor types are actually doing some kind of post-processing, right? There's this nature of a camera that it's ground truth for what you're measuring, right? There's no doubt that what the camera is measuring is the integration of incoming radiance over a pixel over the back of the lens with some like fairly understandable noise model, as opposed to if you do structured light for depth or something like that, you're always kind of like doing this post-processing on the data afterward that's potentially corrupting it in some sense and like removing some of the signal, as opposed to camera data. You can go to a raw image and like that is the source of truth, right? That is the incoming radiance plus a little bit of noise, and that's definitely accurate. I'd also say that even though we say what we care about is image quality and re-rendering and stuff, that's very, very tightly coupled with 3D, right? We saw this in NeRF, where we improved view synthesis quality, and that led to a massive improvement in the types of depth maps and like geometry we could extract for very fine details. And it's not really, I think when you have an underlying 3D representation, even if what you're focusing on in terms of the training loss and the metrics you report is all in image space, it's very hard to make significant improvements there without actually making significant improvements in the underlying 3D. I also just, on the more personal level, I find looking at these image outputs to be very pleasing, right? I think like, we had a big debate about sending this paper to a vision conference versus like SIGGRAPH or something like that, and you might say that like, okay, the images and like the whole like presentation of the thing are more well suited for SIGGRAPH, but what we kind of wanted to do was re-inject this idea of a very high rendering quality bar into the vision community that had gotten maybe a little bit sidetracked by these like very low resolution ShapeNet voxel grids and things like that, and not seeing like how high the bar could be for a neural type 3D reconstruction. Okay, so that was my summary of how NeRF came to be. And next I'll talk about these more recent works as we've pivoted into working on not only reconstruction, but generation as well. Okay, so where are we right now? Like, how good is reconstruction and how good is generation relative to each other? This is another ZipNeRF video, so I think this represents roughly, within some delta of the state of the art of what we can do with 3D reconstruction from images right now. And there's an interesting kind of computational and user-side burden here, right? The amount of work we have to do, right? We just send out code. There's nothing pre-trained here. This is all just reconstructed from scratch from the inputs. But this actually puts a big burden on the user, right? You have to go and you have to take 1,000 images of this scene. You have to have 8 GPU hours to spend to reconstruct it. But then at the end, you get this kind of nice manipulable 3D representation that you can render from arbitrary viewpoints and so on. Versus where we're at in generation, where state-of-the-art models like Sora from OpenAI, they actually have like a very minimal user-side burden, right? You just send a text prompt to this model and you get out something like this. You didn't have to capture any input images. There's no multi-view. There's no nothing. But there's also this kind of insane amount of work being done to create the artifact that can do this, right? We don't know how much, but everyone's speculating between some thousands of GPUs for some weeks or months, and some insanely large corpus of video data probably used to train this thing. But then you get this trade-off that kind of captures the distribution of reality in a sense that you never have to go and take another image again, right? You can just ask this for whatever you want. Okay, so this sort of leads to this like devil's advocate straw man question of, oh, if we have this video model, why do we have to model or reconstruct stuff ourselves? And I think there's a lot of pretty easy counterpoints to that. The first one I would say is that if you have an underlying 3D representation, you clearly inherit one thing for free, which is camera control. And the more you factor out into an explicit grounded representation, the more control you can have, right? You know, if you factor out materials, if you factor out some amount of dynamics, you can control lighting, you can control time, and things like that are not trivial to extract into a generative model. And then more related to what I'm going to talk about right after this is there's kind of this like cyclic nature of reconstruction and generation, right? Where the generation is this stateless feed-forward model that takes some inputs and predicts some outputs, versus reconstruction, and that's kind of single scene optimization framework, has effectively this grounding you can use to extend like the size of the scene, or like, you know, circumvent memory limitations and things like that. And you can also use, you know, reconstruction in a grounded 3D representation to improve the consistency of the outputs of a video model, for example, or an image model. And vice versa, you can use an image or video generation model to guide an underlying reconstruction process, right? You can improve reconstruction by borrowing that prior that's implied by the generative model. So I think there's this kind of like a symbiotic, beneficial relationship that we can observe between these two things. And the first example that I'll talk about is DreamFusion. So I would describe that in this framework as kind of a 3D representation grounding for an underlying 2D generative image model. And this was work done with Ben, Ajay, and John at Google that we presented at iClear last year. Right, so going back to the original NeRF setup, normally we were taking in some large multi-view data set of a single scene, and we're optimizing rendering loss against those pictures. But we could actually imagine, what if we had no images, but what we do have is a massive image diffusion model that understands the world very clearly, and conditioned on a given text prompt can generate lots of images of that concept. And as has been introduced a couple times before, you know, diffusion models are this like rapidly expanding area of work where it's kind of becoming the dominant paradigm for modeling underlying probability distributions of large sets of data, especially in a conditional manner, like text conditional. And of course, there's this framework where you kind of just, what looks like this very simple denoiser is trained to map from a progressively more noisy image to a clean one. And at test time, you can kind of use these sampling-based inference methods to produce a generative sample from the underlying distribution learned by the model. And that results in pretty nice results for image from text in, like, for example, Imagine, Google's internal image model from last year. And the goal in DreamFusion was to turn the power of that model into essentially like a discriminative critic for neural rendering. So I'm not going to get into details of this, but basically it turns out if you just take that single step prediction of the denoising model, that effectively can tell you a pretty good update direction for an input corrupted image. And using that concept, we can directly optimize an underlying NeRF to reconstruct 3D shape from that 2D generative model alone. And for example, this is a reconstruction of the same prompt I was showing in the previous slide with Imagine results of a peacock standing on a surfboard. Okay, so just to kind of quickly describe the pipeline underlying this method, it has a lot of commonalities with NeRF, but there are a few kind of details that we tweaked given the flexibility of not being constrained by an underlying image data set. For example, one is that we don't have a fixed set of training poses, right? We can sample any camera pose we want, and theoretically the image model should be able to understand what an image from that viewpoint should look like, because it's kind of learned this distributional set of images. So we sample a random camera. We are again doing single scene optimization or reconstruction, so we learn one NeRF MLP for each text prompt we want to model. And in this case, we don't use that view-dependent outgoing appearance model. We use an underlying fixed RGB albedo model with a simple Lambertian shading on top. And that's because we're not bound by the particular lighting conditions of any captured input data. We basically can, like, again, exploit the space of what's learned by the underlying model to change lighting arbitrarily. Okay, so we take that density field, we extract some sort of normals to do shading. We do n.l for Lambertian shading. And then we apply that to the albedo to get an output shaded image here. That gets noise added to it, that gets sent through the Imagine model, and that predicts a final denoised output, which we then convert into a gradient update for the underlying NeRF. So we backpropagate that onto NeRF weights. That's a single optimization step. In DreamFusion, we did this for around 15,000 steps. I think a lot of more recent work has figured out ways to do this in very few steps or even in a feed-forward manner. But at this time, we had this model knows nothing about underlying multi-view data, so there's a lot of high variance in the updates, and it takes a while for it to converge. Right, so then this lasts until we get a nice model out at the end. And again, this is using this Lambertian BRDF assumption, so you kind of have this relighting effect you can do because it was trained with random point lights. You can render it with an arbitrary point light, and it still looks reasonable. And one aspect of that I wanted to just mention was we actually saw a lot of improvement in geometry from switching from a strictly NeRF-based like volumetric view-dependent appearance model to this Lambertian shading model, because that actually exposes much more of the geometry to the image generation model itself. So it kind of can see if there's a lot of gross like NeRF fog artifacts or all this like bumpy stuff, because when you change the lighting, the n.l term will just like directly expose that as the light moves around. And that ends up smoothing the surface a lot as a nice regularizer. Right, yeah, to be compatible with a random point light, you actually need to have better geometry. So this is a bunch of generations we made from this. I think the final website we had around 400 example outputs, which funnily became this sort of like prompt data set for other people, even though it was just our cherry-picked prompts from Imagine that happened to work well. We also were inspired, since obviously we couldn't butt up like a live demo of this because it took like 45 minutes, we pre-baked a bunch of prompt combinations together to combine these like different types of squirrel with different activities and put that up. That was inspired by I think the DALL-E 2 website. And again, as many people observe with NeRF, you can use marching cubes to bake the density field into an underlying mesh. And that gives you pretty nice reconstructed geometry that you can use in a mesh viewer online, or people were even 3D printing these things in some cases. And just a couple of quick observations and why this happened in our group when it did. So previously, the same exact group of people had worked on this DreamFusion paper, which was basically the same idea, but instead of having this really nice diffusion-based regularizer, we just used clip loss. And this was actually inspired by a bunch of kind of like deep dream, like 2D generative art stuff that people have been doing in 2021, taking VQVAE and VQGAN, which were like these awesome open source image models that had just come out, combining those with a clip cosine loss against the text prompt to produce these kind of like trippy, psychedelic, deep dream-like outputs. And we were like, oh, we can use that for NeRF. We can use that as an easy 3D loss to minimize. And we got this kind of very conceptual outputs essentially compared to what we got in DreamFusion. And then, after we had done that, Ben and Ajay kept working together, and they both have done a lot of really cool foundational work on image diffusion models. So they knew the promise of these models even before DALL-E 2 and like Imagine were public, and they were really looking hard for a way to use them as guidance in 3D. And again, I like to think of this in this framework where this is not really pure generation, right? We're actually borrowing all of the standard single scene optimization reconstruction framework that NeRF has and just applying a different loss at the end of it. And again, I think the reason we were able to pull these persistent 3D reconstructions out is because we did have that grounded 3D model backing this. Okay, so after this kind of pure generative text condition work, we were thinking like, how can we use this kind of thing to improve NeRF reconstructions when we do have some kind of input image data, like maybe some sparse multi-view data. And in this context, a lot of work happened in the year and a half after DreamFusion to augment existing text-to-image models with some kind of knowledge of multi-view information in the form of camera pose. And I think we can classify these roughly into two buckets, right? There's these kind of weak pose condition models that flatten out the pose and just use cross-attention on the direct matrices, like 0, 1, 2, 3, and 3dim, and a bunch of others. And then there's this kind of stronger pose conditioning where you actually do use a pixel NeRF-like feed-forward model to do some kind of 3D prediction, and then you essentially use a diffusion model on top to super resolve or like clean that prediction up, right? So like GenVS, NeRFDiff, and a few others. So in this context, we were thinking, okay, how can we use one of these more like multi-view aware image prediction models to regularize reconstruction really well? And that led to this ReconFusion work, which we did last summer. And this was led by our intern, Randy Wu, and me and Alex were also working a lot on it on the implementation side. So okay, we again borrow the basic NeRF setup, but this time we have this additional constraint where we assume you have very, very few input views here. So normally for a scene like this, I would tell someone, if you want to capture this bench, go take like 100 pictures at least. But in this case, if you drop it down to 3, 6, 9 inputs, this is actually almost such a bad failure that it's hard to understand. Mostly what's happening here is the bench is being painted onto the kind of infinite distance environment map, and you're just seeing each of the 6 pictures reproduce, which minimizes training loss perfectly well because there's so little multi-view overlap that you can get away with doing this. Okay, so that's obviously a very bad failure, and we want a strong regularizer that can prevent something like this happening by regularizing over other views besides the 6 observations. So as in DreamFusion, we want to be able to sample a random camera pose and then use a diffusion model to critique that pose, essentially, and say, does this look like a real image, or does this look like some garbage? So we were thinking, okay, which of these multi-view pose models is suitable for this task? And we ended up settling on a model. We tried both kinds of weak and strong pose conditioning, but the thinking here was that reconstruction is this like very metrically precise task, right? We're relying on the intersection of rays, we're relying on pixel perfect alignment of cameras and so on. So we're going to use one of these models that very explicitly does a reprojection step and a 3D prediction step before feeding this conditioning through to the underlying diffusion model. So we ended up with this very GenVS-like architecture where we essentially had a sort of small pixel NeRF module that took the nearest 3 inputs out of the observed images, rendered a novel view at a new pose, and then concatenated that feature image as input to a stable diffusion-like UNet. So once you have that predicted output at the novel random view, in this case, we didn't actually even end up using STS. We actually used a more image space loss. I think it was a combination of L2 and LPIPs to compare these 2 images and directly backpropagate onto the NeRF like it was a real view that we had actually observed. And just a quick comment on the training of this model. So I think most of the existing models of this form that had strong or weak pose conditioning are usually trained on a single category or only Observerse or only fire hydrants or something like that. We specifically wanted this model to be the same prior for any scene we captured, right? We wanted it to be the same for our real estate 10K walkthrough scenes. We wanted it to be the same for co-3D object capture scenes. So we actually just trained it over all these data sets at once and hoped that it would generalize well. And here's an example of how this works in practice, right? So you have some sparse number of input views. This is a sparsified MIPNERF 360 data set capture. If you reconstruct it with ZipNeRF with no prior, again, it looks terrible. If you look at the samples coming from our trained strong pose conditioned diffusion model, they're actually not great either, right? These are pretty inconsistent relatively, but you can see that when the shape emerges, it's on a stable orbit, right? These kind of look like NeRF renderings plus a ton of weird high frequency corruption. And in particular, the high frequency details are hiding in there, right? You're getting these reprojected high frequency details from the input images that are captured by the diffusion model. So if you kind of combine all this together, you can get, it's on a per frame basis, it actually does end up being a little bit worse than the specific predictions from the diffusion model, but it's clearly much better than basically it was a totally untenable situation before. Right? We had no chance of reconstructing this with the input images with no strong generative prior, and now we can kind of resolve this object in the center of the scene clearly. And we did a quantitative evaluation of this behavior with the kitchen Lego scene from MIPNERF 360. So, again, this has, I think, 270 captured images in the original data set, and we were sparsifying it all the way down to 3, which I would have guessed would never work when we started this project. So I was, very excited to see that we actually got decent performance on 3, 6, 9 images in this context, because that's sort of been this barrier. I would have always thought that would not have been possible before. And once you move to 6 images, you even start to get to a pretty reasonable reconstruction, right? I think it's still not, it's not close to the level of what you have with all the input images, but it's starting to look like it's passable, right? At a qualitative level, it looks pretty good. I think a user could even be potentially okay with this kind of level of quality. And once you move up to a large number of views, you might expect that ZipNeRF would fully catch up by the time you get to 81 views. But you actually still have a lot of these annoying kind of volumetric floater and fog effects that sneak into the reconstruction even with this level of sampling. And even those can get kind of cleared out easily by this generative prior because it knows they shouldn't be there. And again, yeah, this is definitely, I would not claim that this is the best multi-view post-conditioned diffusion model in the world. I think we are tackling a much more general and harder task than most of the models that use Observerse or only Co3D, because we were trying to work on arbitrary scenes and capture types. But I do think there's a ton of room for improvement here. It's actually not too expensive to fine-tune this model into existence, so I think there can be very rapid fixes to this kind of thing to make the underlying reconstructions even better. I'm going to quickly skip over this because I'm almost out of time. But we were very happy with the extent to which this generalized to, in particular, we ran it on a lot of Co3D examples. And there's kind of this, I think, preconceived notion that like, oh, Co3D is hard to reconstruct. Like the captures are, there's these user-sourced captures, and they're not super high quality. There's a lot of like blur and a lot of like camera pose problems. But it turns out that you can sparsely subsample the views down to, I think these are probably 6 or 9 inputs, and you can actually apply this kind of prior and get a pretty nice reconstruction even from that type of chaotic data. So okay, what's next after this? Obviously, we can all tell that the fusion models are getting a lot better all the time. Not just image models, but for sure video models with Sora and these kind of post-conditioned multi-view models are all improving very, very rapidly over the last year. I think 3D distillation has also seen some improvements, and I would almost describe this as like it's reconstruction in disguise, right? It's using reconstruction to ground the generations of a model, and that's been improving too. And we're seeing a lot of works that focus on exploiting the 3D signals you can get when you're doing this grounded reconstruction, right? Like just like Ling Jie said yesterday with Wonder 3D, once you're doing a NeRF reconstruction, you get depth, you can get normals, you can get all these signals for free. You can incorporate those into essentially a consistency loop with a diffusion model that's been trained on those type of priors to get better results. And I think we're also seeing like people investigate the scope of what kind of particular conditional controls can be learned by an image or video model, which is really interesting, right? We see stuff like, there's this paper motion control that's trying to factor out camera motion and scene motion into 2 separate modules and control them one at a time. There's this other work, loose control, which I thought was really interesting, where they actually create a bunch of training data by, they exploit like monocular depth and stuff to build these kind of loose bounding boxes that then actually serve as a much more kind of casual form of conditioning than an actual depth map, for example, right? This kind of box conditioning is something a user could feasibly lay out and set up themselves. You're never going to paint a full depth map, but you could actually easily do this kind of 3D control directly. And again, if we go back to the Sora video, after I saw this, I was like, okay, I got to try to NeRF that because that looks really 3D consistent. And it turns out, yeah, it's really 3D consistent. Like, I've seen some examples on Twitter of people drawing like vanishing points and stuff that are not quite there. But a lot of these static video generations that come out of Sora actually are totally 3D reconstructible. A bunch of people have verified this with, NeRF Gaussian splatting on various of the different videos posted by OpenAI. And I think, I see that as a very promising sign for the future. I think like where we're going is kind of this application-specific direction where it really depends on what level of control the user wants, right? If all the user really needs is to take text and map it to a video, that's fine. But I think a lot of people are looking for a more fine-grained degree of control, especially in like spatial layout and camera position and things like that. And we're going to see people who just demand that level of precision. And I think that's like actually a fairly large like middle group of people who are going to say, I'm not happy with what I got out of pure text. I want to go and I want to like change something. I want to go and edit the layout. I want to go and like insert something new without disturbing the rest of the scene. And I think 3D grounding for, as a direct representation or as a form of control could be really useful for that. I also think, there's this kind of funny thing with inverse problems and reconstruction and generation, right, where we're separating out like, okay, if you have an observed captured image, that is a condition for reconstruction. That is an observation for reconstruction versus like, a concatenated input image to a diffusion model, maybe we call that a condition, but like at some point these lines are going to be very blurry, right? Like, what is strictly a conditioning signal versus an actual like L2 reconstruction signal? I think there's a lot of room for exploration in that space. And just getting back for 30 seconds to the title of my talk here, I was hoping to kind of allude to like, I think there's this very fruitful combination of what's happened in both the reconstruction side and the generative model side of the communities, where you can combine the power of both of these things to create very, very high quality reconstruction pipelines that have much lower data input requirements than required before. And I think this also can lend progress to very data restricted problems like full inverse rendering, decoupling material and lighting, where in theory you would want like a lot of disentangled lighting and camera measurements, but it's really just not practical to densely measure that space. So I think using these generative models as discriminators or critics can actually serve to improve that kind of work a lot in the future. All right, thanks.
Thanks so much, Ben, for this amazing talk. We're slightly late on schedule, but we have also a shorter session now upcoming, so we can take a few minutes for questions if anybody has any.
Hello. I want to say that tidbits slides, yeah, I'll take a photo. Yeah. Okay, thank you. I'll check that later.
It's all technically in the paper, but.
Hi, thanks a lot for the talk, Ben. Can you tell me, please, about what do you use for conditioning to create the 3D shape? Do you have just several images and you just like feed it into the diffusion model, or you transform it first to some latent space, or you do something else with the images? Thank you.
Are you talking about the model in ReconFusion that we trained?
Oh, yeah, that's right.
Right. So it's very similar to GenBS and other methods like that. So we actually have this whole kind of pixel NeRF-like module where we take 3 of the actual input images to the scene, like the observed reconstruction images, and you create, essentially you're creating like a plane seat volume. Like you trace rays, you reproject the rays, gather features from the input images and pass them through a small MLP that creates a kind of pseudo NeRF-like representation. So you're actually doing a pretty extensive 3D processing to create like this novel view feature image from the new viewpoint. So you get this like new image that's very well aligned with the output you want to generate. Yeah.
That's great. Thanks.
Hey Ben, thank you for the great talk. Since you mentioned the cyclical nature of how doing this reconstruction improves the generation and how generation can now have much improved controllability and consistency, I wonder to what extent you think that as the generation gets better and more realistic, can we ever reach the point where we just treat generation as a simulator that simulates all of physics and all of camera control, like everything in the world can be just synthesized by a generative model, and like all future applications will just use this generative model as a simulator. Do you have any thoughts on like whether that's possible or what our progress is like towards that?
Yeah, I think after Sora, I wouldn't be totally comfortable saying it's impossible, but I think that I would not say it's not annoying, right? I think like the more, thinking of training all these kind of forms of conditioning into the model, right? You have to train in camera control, train in like scene motion, train in all this other stuff. And I think every one of those things is just an extra module that you have to add and find like data for, and maybe have like sort of self-supervised annotation. But yeah, I think like of course stuff like simulation may just emerge from like seeing a million videos or a billion videos or whatever. But I think like these kind of user-side controllability aspects are not something I would expect to come for free, right? It's going to be tedious to kind of like bake these things into conditional signals, and you're seeing that, right? There's like 50, 100 papers that are baking in motion control to different ways into video models, and it's not entirely clear that like that is the most intuitive way to extract this data, when maybe it can just sort of fall out for free if you have a grounding representation like with a reconstruction loss that can kind of extract it from the model in a grounded way. Yeah, we'll see.
Yeah, thank you so much for the great talk. So it's kind of related to this question, but more toward basically 4D now. So it's basically mostly static scenes right now. But with Sora, basically, we can see that we can generate very good videos, potentially multi-view videos. So where do you see basically the NeRF-like models going towards 4D scene reconstruction?
Yeah. I mean, I think my prediction there is that like this will probably be the thing that solves monocular dynamic 3D reconstruction. Like I think like that was always very similar to like material lighting decomposition. It's always an ill-posed problem, right? Just the nature of data you can easily capture. Most people don't have more than 2 cameras on the back of their phone. You just don't have multi-view observations at all points in the sequence. But I think these kind of video models are going to be very, very good at synthesizing plausible missing views or acting as a kind of a discriminator for those missing views, given what we've seen. So I would not be at all surprised if within like a year or so, people basically apply this to monocular dynamic reconstruction. We see massive progress. Yeah.
Hi. Thanks a lot, Ben, for a great talk. I have a question regarding the kind of how you see the outlook compared to, NeRF was kind of the dominating implicit 3D reconstruction in the last 4 years or so, but last year Gaussian splatting came up, and now it's like kind of the big hype. I was wondering what's your view on how you think this will evolve in the future? What kind of competitive kind of advantage of like all the NeRF work that's been developed over more time, let's say, how that will kind of interact, or like how can it evolve with the Gaussian splatting work that we are seeing?
Yeah, I mean, of course, I think this has been a big topic of discussion this week for me, for sure. And someone made a very nice analogy that I liked a lot to physical simulation, right, where you've had Eulerian and Lagrangian, like grid and point-based methods kind of coexisting for essentially decades at this point, with a lot of interesting hybrids emerging for particular applications. I think there's a clear analogy here where, like, you know, it's obviously more convenient to have these kind of explicit point-based representations in a number of applications. And in particular, like, it becomes this kind of like, it's instantly baked into a real-time representation, right? As soon as you optimize the thing, you go and you can put it in a web-based renderer on like any device, and it just goes. I think like probably the trade-off comes in terms of, like, there was just a paper today from Federico's group at Google on this kind of, you could pre-train a very high-quality NeRF model and then distill that into Gaussians, and you get kind of the best of both worlds, where you get the very nice optimization dynamics of NeRF, and you get like the fact that you can do ray tracing and arbitrary camera model and things like that, whereas the rasterization-based framework comes with certain restrictions. You know, in graphics we've seen a similar story play out over the last 20 or 30 years, where rasterization and ray tracing have kind of been like fighting in various contexts, and like there was all these hardware limitations which have recently been sort of like circumvented through like massive amount of like engineering and brute force on NVIDIA's part to enable ray tracing in real time in video games. But yeah, I think like rasterization it's so easily supportable by the hardware we have now, and it's going to take a little bit of work to get ray tracing, and it's like harder to fit into like a fast framework natively. But yeah, I think I'm guessing we'll see, you know, a lot of work as it's been happening immediately just swapping in Gaussian stuff, and then over time like an eventual convergence of like, okay, maybe there's some spots where a grid-based method is still convenient. You know, we'll see what ends up happening with feed-forward methods too, where you're predicting like an output. Should that be a grid? Should it be points? Who knows? So I think it's a tumultuous time, and I would predict seeing like, obviously for real-time rendering, the point-based stuff is just so clearly easy and fast to use that we'll probably see that for a lot of these kind of like baked out things. But for optimization and feed-forward prediction, we'll see what happens. I think they might both kind of coexist for a while.
I think we have time for one more question. Maybe can you reach the microphone over there? Then it's time to wrap up.
Hello. So thanks for giving me a fun question. So basically, we humans also see an impure 2D, and yet basically everything we see is, well, a 3D scene. It definitely has to do with, of course, having two eyes, of course, but if you see just one single image, you also have that kind of complete 3D feeling, which would be identical to simply a single view reconstruction of a whole 3D scene. So my question is, do you think the capability of us humans in this respect more resembles the, for instance, consistency we see currently in Sora? So basically having enough experience with the world and therefore having an implicit prior of reconstructing it? Or is it more related to perhaps having more explicit like raycasting or explicit physical recognition of how the world works that can be modeled more with NeRF or 3DGS? So in other words, which of those do you think is more predominant in forming our ability in this respect? Thank you.
That's an interesting question. I think people like to draw a lot of analogies to what they think is happening in human visual processing and like people's ability to, you know, think and do 3D reasoning. But personally, I don't think it's clearly not true in a metric sense, right? You don't see a chair and you can tell me like the length of the back leg of the chair in centimeters. I think it's actually probably a lot more similar to Sora, essentially, where people are, you know, if you show me a video, I can tell you if it looks like a consistent 3D scene. I can't draw artistically that thing. I can't like extract measurements from my mind about it. But I think like that doesn't necessarily inform what we should do as computer scientists, because like, you know, computers are actually very good at a lot of things people aren't good at. And like the fact that they can achieve this kind of large-scale grounded 3D representation and reasoning, I think has a lot of useful aspects that can like augment what people can do in a nice way. So yeah, the neural stuff, like, you know, I'm no neuroscientist, but like I know I can't like canonically predict the back of all your heads right now. But yeah.
Thank you very much.
Great. So we have to wrap up the session, thanks again, Ben, for this incredible talk and all the Q&A.
Thank you.